All right, here is the lesson 9.2a notes, but we're actually going to start off with wrapping up 9.1c just a bit more before you take the quiz. So I'm going to continue that example that was in the warm-up about the potatoes. So for example, potato chips. We're going to inspect a truckload of potatoes to see if they're good enough for our potato chips. And specifically, I want to do an example of the consequences of the different types of errors. So we take a random sample from this truckload. We count the blemishes on the potatoes. And we decide in advance that if there are 8% blemishes, that's okay with us. But if there's more than 8%, we're going to reject the truckload. And some books actually do this as a less than or equal, because maybe we have less than 8%. That would fall under the null hypothesis. So P is the true proportion of blemished potatoes. I love that word blemishes, don't you? In the population, which is the whole truckload. All right. If we reject the null, that means we decide that this is true. We decide there are too many blemishes for our potato chips that have to be perfect. And then we would send them back. Don't use this truckload. All right, type 1. Let's talk about consequences of type 1, or specifically, what does it mean in context, and then what would be the consequence? So type 1, you're going to memorize, if you haven't yet, that this means the null is true, but we reject it. That means the null is true. Let's put that into context. Null is true means there really are less than or equal to 8% of the blemishes. Got to write that word again. But we reject it, which means we think there are more. Why would that happen? It would happen because our sample had more than 8%. And it's far enough more than 8% that we find it significant, so we send it back. So because we are rejecting, we think there are more, that means we send back this truckload. But remember, there really were less than 8%. So it really was a good truckload of potatoes. We just got a bad sample. The consequence of this is we wasted a truckload of good potatoes. We didn't use them even though they were good. It also wastes time and money because we got to get more potatoes. There's always money involved, right? So type 1 is wasteful. We're throwing out things that don't need to be thrown out. All right, type 2. Let's do the same thing with type 2. So we're going to start with the definition, and then we're going to put it in context, and then we're going to think about the consequence. So, by the way, there is a question on the quiz like this, which is why I'm going over this one more time. So null is true would be type 1. Null is false would be type 2. But the error would be we don't reject it. So what does that mean in context? Null is false means what's really true is the alternate. There really are more than 8%. with blemishes, but we don't reject it because we think there are less. Than 8%, or we think there's exactly 8%, or we just don't think that there's more because our sample came out better. My sample, the sample has more than 8%, or sorry, less. Sample had less than 8%. And so we're thinking this truckload is okay, when really if we had taken a bigger sample, we might have found out that it really had more than 8%. So that's the context. I should put that, we're doing the context. Describe it in context. I prefer to describe it without context and then translate. Without context, translate into context, and then the consequence. Well, what would that do to my potato company? It would be taking in this truckload full of potatoes that are bad, even though I think they're okay. And so I would use this truckload to make potato chips, and my potato chips would not be very good quality. I'd have bad looking chips. And maybe my customers would complain, maybe they would switch to a different brand. That would be bad. I might lose some customers. So that's basically the idea behind this type of question. You need to be able to translate from the definition into the context and then talk about what that would cause to happen as a result of this error. Would it cause you to throw out good potatoes, or would it cause you to use bad potatoes, or what would that cause? So that's an example of a type of problem that is pretty common, and there will be something like that on the quiz. So I wanted to warn you about it. All right, lesson 9.2a. Now we'll do 9.2a. It's not actually very long what we need to do for this. So we're going to talk about, finally, how to calculate the p-value. I've hinted at it, but we haven't actually done it much yet. So calculating p-values, we're going to start with proportions because that's what 9.2 is about. We'll come back to means in 9.3. And so I'm going to go back to Noel and Alan because I really like that example. Go back to Noel and Alan. Again, you don't mind, do you? Of course not. So we've got the free throw thing. And just to remind you that the null was what Noel said, which is that p is 0.8. The alternate was what Alan said, which was p is less than 0.8. He didn't think she could really make that much, and p is the proportion of successful free throws. I realize we've written this before. I'm just trying to be thorough. All right, so that's the review part. Now, let's say we gather some data. Of course, we make her do some. And she happens to shoot 32 correct ones out of 50. That's successes out of attempts. And that's our p-hat. P-hat, which is actually 32 out of 50 is 0.64, which is kind of on the low side. Did I do 35 last time? I don't remember. It doesn't matter if I did 35 last time or not, but I'm going to do 32 this time since I already wrote it. So we're going to find our p-value, which is officially the probability of getting this result or worse, given that this is true. So I'm going to write that in symbols. Probability of getting a p-hat of less than or equal to 0.64, given that the real value is 0.8. So probability of this sample result or worse, given the null is true. That's what I want to calculate. So basically, because I'm saying given the null is true, I'm picturing in my mind a normal curve with a 0.8 at the middle. And I'm going to calculate the standard deviation so that I can figure out just how far off is that 0.64 that's down here somewhere. And I'm going to find this area. That's what I'm about to do. We have done this before, starting in chapter 2, and then in chapter 7 is where we learned how to find the standard deviation. So I'm going to do all of that. Hang on, I need to make sure my computer didn't die. It seems to still be recording, so that's good. So to find this probability, we're going to use a z-score and a normal CDF. And the z-score, instead of doing x minus mu like we started off with in chapter 2, I'm going to say it is going to be our sample value minus our hypothesized value. So it's always going to be in this chapter the sample minus the hypothesized parameter divided by the standard error, which we know how to calculate. Actually, I guess it's called standard deviation in this part because we're not going to estimate the standard error from p hat. We're going to calculate it from p since we think we know what p is. So we're doing p hat minus what we think p is. I'm going to call it p0 because we don't know for sure if that's p. And we're going to use that p0 value that came from our null hypothesis to calculate the standard deviation, which remember is the PQ over N that we learned long ago. So P0Q0 over N, we're using those numbers from the null hypothesis to get as accurate as we can on this normal curve. Okay, so let's do the details. P hat is 0.64 minus P0 is 0.8. We're going to use the 0.8 again down here. 0.8 times 0.2 over, there were 50 free throws. And you did this in the warm-up, I think it was Monday, and I didn't fully explain yet, but I'm going to explain further right now and say this is a different standard deviation than the one you use for a confidence interval. Remember, for confidence intervals, we use the p hat, which, by the way, I remember now that it was 0.7 in the warm-up, but that's okay. So we're going to find the standard error. I'm going to go ahead and find that first, actually, which is the 0.8 times the 0.2 divided by 50, and then square root it. And I got 0.0566 on the bottom. On the top, I have a negative 0.16, and I'm going to divide that. And I got negative 2.828. That's my z-score. So I'm going to find a z-score based on the assumption that this number is correct. That's what I'm doing. I'm using this normal curve, and I'm going to say, okay, that means that this piece right here is 0.0566, and I'm trying to figure out where 0.64 lies on this. It's actually almost negative 3, so I should have drawn it further over. I can see that this is going to be significant, and that's because 32 is less than what we used before, which was 35. Find the p-value. The p-value is the probability of getting this much or lower. So that would be a normal CDF, where you could use table A if you like table A better. And we want to go this much or lower, and that's because this is a less than in our null hypothesis or alternate hypothesis. If we were going greater than, we would have to go the other way. But I'm going to go negative something big and negative 2.828. And I'll use that to find my p-value. Normal CDF, negative 999. Well, the calculator default is that, 0.2, negative 2.828. Got it. And this is 0.0023. Really small p-value. Less than 5% by a lot. Therefore, we would reject the null. And we've already talked about that. So that's how you calculate a p-value. You figure out the normal distribution, you figure out the mean and the standard deviation based on your given, which is your null hypothesis, and then you find the z-score and do normal CDF. And you've done that before. I hope you're getting really good at it. And notice it keeps coming back. Anything that comes back over and over again is something important. And I have one more thing to talk about before we stop, and then we're going to do a quiz next. Crazy. Last but not least, what if my alternate hypothesis has a not equal sign instead of less than? So this was a less than, which is actually the easier type to calculate. But sometimes we don't know which direction it goes. It could be less than, it could be greater than, we just don't know. And then we do what's called a two-sided test. Or sometimes it's called two-tailed. And I'll show you on a normal curve. No big surprise, right? If it's a not equals, then that means that we're interested in this much or less, but we're also interested in this end. If it came out over there, we would also reject. So we would reject if it was too low or if it was too high. And that means we have two tails. Two tails. That's why it's called a two-sided or two-tailed test. We have two tails to think about because those two tails have to be less than 5% put together. And that doubles our p-value. So if you are working with a null hypothesis, actually not a null, the alternate hypothesis that is two-sided, you have to double your p-value. So I would take this 0.0023 and I would double it and get 0.0046, which by the way is still less than 0.05. And I would still reject, but sometimes that would make a difference in my answer. Or in other words, the two pieces put together have to be less than or equal to 0.05. You're actually more likely to reject with a one-sided, and that's interesting. Both tails, I should write this, put together must be less than alpha to reject. It lowers the power of your test just a bit, but sometimes it's more appropriate depending on the context. So we're going to stop there and we will do more next week. And the second half of today is all about the quiz on 9-1. You will not have to do these calculations on the quiz. I should write that also. This whole thing is not on the quiz. There you go. And that's it for now.